So welcome to the, it's a nice view of the ceiling there. Welcome to the last but one London Learning Lean. Next week it's of term. Next week it's Rena Robson who's going to tell us about post-quantum crypto. But this week we're very pleased to have Yaël Dillies, stuck in Cambridge because of the train strike, who's going to tell us about Behrend's construction and additive combinatorics. Over to you.
Yeah, thank you very much, Kevin. So maybe I should share my screen actually. Can you let me share my screen? I cannot see. Yeah.
Yeah, it's all right. I need to. Sorry, I'm logged in too many times. Make co-host. There you go. Now you should be fine. Sorry about
that. Yep. Perfect. Does this work?
Yes.
Perfect. Okay. So I'm going to talk about well, several things. I first want to start explaining one of the very first theorems that we got from additive combinatorics, which is called the van der Waerden theorem. And this theorem is about sets of naturals. Actually, yeah, I mean, if you are not British, you will start at 0, but that doesn't change much for our purposes. So this is the naturals. And imagine we color them in like n colors. So let's take some bigger brush. So I put those red, for example. And then I will put those blue, something like this. Okay, and it goes on forever. Then what van der Waerden's theorem tells you is that for any natural number k, you can find a color among red and blue, and an arithmetic progression of that length that you decided, k, such that all the points in that arithmetic progression have this color. And this works for an arbitrary number for an arbitrary length and for an arbitrary number of colors. This was proved in the 1930s, and back then, Josh had the thought that probably like the colors were not the interesting bit, in the sense that if the stronger theorem of instead of having colors, you have only one set, and you know that its density is non-zero. So what I mean by density is natural density, which is let me write it. Yep. So the density of a set S is equal to the limit as n tends to infinity of the number of elements of S less than n divided by n. So typically, the density of the even numbers is 1/2, just as the density of the odd numbers. And the density of the prime numbers will be equal to 0. Stuff like this. So now, this is we get if we replace this statement of van der Waerden Actually, is it maybe van der Waerden? I'm not sure. By the stronger thing, which is now called the Szemerédi theorem. Szemerédi, yep. So you still have the natural numbers, but now instead of having colors, you have just a set. So now if the density of S is greater than 0, then for all k, we can find an arithmetic progression of length k within S. So this begs the question of how big can a set be if it doesn't contain arithmetic progressions? So this means the Szemerédi means that the density of rather see if S has no arithmetic progression, then the size of S, or rather the size of S divided and 0 to n minus 1 will be little o of n. Because if it was not little o of n, then it would have a strictly positive density, and Szemerédi will give you an arithmetic progression in there. But actually, we can do so we know that it's little o of n, and if we think about, for example, the greedy algorithm. Let me extend that a bit. Perfect. So if we think about the greedy algorithm, what does that give? So you will take 0. Then you can take 1. Oh, by the way, we will restrict to so for the purposes of this talk, we restrict to k equals 3, because this is actually a very hard problem. And k equals 3 is the only thing that I have proved it. When I say I have, it's actually rather, as always, it's rather Bavik who proved it. But I just happen to be particularly stubborn in putting it into Mathlib. So I don't know. It's a joint work with Bavik proving the things and me PRing them. So if we restrict to k equals 3, we take 0 because there's nothing yet. We take 1 because there's no arithmetic progressions of left 3 possible with 0 and 1. And then if we take 2, then we get 0, 1, and 2, which is an arithmetic progression, and that we don't want. So we skip 2. Then we take 3. And then with us, I mean, we can quite easily see that we can actually take 4. Then 3, 4, 5 would be a problem. So we do not take 5. And now if we take 6, we see that it will be a problem with 0 and 3. So we do not take 6 either. But we can take, and we can't take 7 either because of 1 and 4. And now if we look at 8, that's still not possible. And finally at 9, we finally hit something which is possible. And if we keep on doing like this, we see that actually what we get is the numbers, the natural numbers, such that there is no 2 in the ternary expansion. Okay. So how many of those are there which are smaller than n? Well, if we think about it a bit, we have for each form. So if we take n is equal to 3 to the k to simplify, then for each of the k digits, we have 2 possibilities, namely 0 and 1, because the only thing that we can't do is take 2. So the size of S of Sn, which is the set, which is this set up to n, will be equal to 2 to the k. which is e to the how do you want to write it? So it's equal to yes, it's equal to n to the log 2 of 3, sorry, log 3 of 2k. Of 2, log 3 of 2, yeah. So we get something which is sublinear as expected. It has to be little lower than. But it's not, it's quite far from being linear. So can we do better? And the answer is yes. And this is Behrend's construction. So this is 1946, which is quite old when you think about it. So Behrend's construction starts with the idea that to find a set in the naturals, which doesn't have arithmetic progressions of length 3, it's enough to find a set in n to the d. Because then, if we have such a set, so this is n to the d, and I have some set here, what I can do is to send it to n by taking the first component. Well, first, if we have a set which is bounded, so we'll actually assume this is a box rather than a fair n to the d. We only care about finite stuff anyway. So we can map the first component. So if we have like here, let's call it a0 up to ad minus 1. We can map that to a0 plus a1k plus ad minus 1 up k to the d minus 1. And this this map is linear. So what you you know that if you get an arithmetic portion at the end, you had it at the beginning, except possibly if when you because you see this is reading the k-ary expansion of this number. So the digits could carry. So to make sure that the digits don't carry, we'll take k greater than 2d. Sorry, is it the? Sorry, so this is sorry, I will call that c. So k has to be greater than twice the size of the box. And this is fine because this is a constant factor of 2 to dd that we're giving up. And we only care about asymptotics. So in the end, if we take, for example, if we look at the image of the entire box, it will be something like this. So some interval of naturals, and then we skip a bit, this like that, and then we skip. So let me so this will be C. And then we skip even more. So this is 4C. We skip even more of 4C again. And then we start doing it again. Doop, 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 doop. And then we skip 8C, etc. So it's quite sparse, but in some sense, it's sparse only by a constant factor, which will disappear in the end. And now we were reduced to the question of are there big sets without arithmetic progressions. In N2DD. And this is where Behrend had his insight. Namely, that actually, yes, there is such a set, the sphere. Because if we take the sphere, so of course it's not a set in N2DD, but that's a technical issue. And we take a line, then it will only hit the sphere in 2 points. And arithmetic progressions form a line. So there is no way we can have an arithmetic progression on the sphere, because that would be 3 different points in a line in the sphere. Hence, we have a strategy. Take the sphere. So this is not a sphere. Sphere. Intersect it with N2DD. So that gives us a bunch of points on the sphere. Then map it to N. And that gives us something like this, as we've seen before. And to get many points, to not lose that many points on the first step. So this is step 1 and step 2. So step 2 is already okay. Step 2 doesn't lose much. Okay. And step 1 doesn't either if we use the pigeonhole principle to pick, not only pick the to pick the radius of the sphere that we're taking. Because we can take all the radii of the form root of n. And all those will hit the points of integer coordinates of distance less than n from the origin, less than root n, I would say. And we know how many there are because this is a standard thing about the size, about the volume of the sphere. And then we get a lot of calculations. That actually our set is of size n over e to the big O of root of log n. Which is much better than the n of log 3 of 2 that we had before. So let me tell you something about this before I show you the lean code. We use something pretty important, which has a geometrical significance to run this argument, which is this: the fact that the sphere intersects a line in only 2 points. Because this is actually not always true. If we take, for example, so I will go sideways here. In L infinity, the sphere looks like a cube. And then it most definitely doesn't intersect all lines in only 2 points. So what's important about this? Well, it turns out it's a property called strict convexity. String convexity is the fact that if you if you remember the convexity, so convex is for all xy in S, and AB greater than 0 such that A plus B equals 1. Then AX plus BY is in S. So this means that if you take something like this and you pick 2 points, then the entire segment lies in it. But it can also lie on the boundary.
Wait, yeah.
Nothing is topological.
I had a question.
Yes.
So why are you using other L norms? So like, would it help in this proof to use, I don't know, L3 spheres in order to do this? I mean, I guess you could do the same kind of trick with cube roots or something.
Yes, absolutely. As it turns out, it doesn't give you anything in the numerically. It will only give you the same result by a constant factor.
I see.
So yeah, it's interesting because we actually have all sorts of geometrical constructions which are kind of derived from this one, but they do not really use like another space. They use the same space but in different ways. I mean, I will come to it in 20 minutes or something when I reach the other part of the talk. So yeah, convexity is the segment lies in the set if the endpoints lies in it, and strict convexity is basically the same, except that instead of taking non-negative coefficients, you will take positive ones. And you strengthen the conclusion to the fact that it lies in the interior.
Because A plus B is 1, right?
A plus, yes, yeah. Absolutely. Can I? Yep. A plus B is 1. So the picture is that, for example, the circle is strictly convex. If I can draw it properly. But the square isn't. Because if we take these corners, for example, then the entire segment doesn't lie in the interior of the circle. So convexity is really just like a property belonging to vector spaces. Strict convexity is something about the topology as well. Okay, so now the interesting thing is that strict convexity wasn't a thing in MATLAB when we were first proving this. So we had to make it one. And as it turns out, there were many things using which ended up using strict convexity. And like this is actually quite far-fetched, but the FLT regular project used it because they needed a fact about complex numbers, namely the so it's not that PR, it's the previous one. Nope, not that one. Oh, sorry, I missed it. Okay, so they needed. I will just write it down. They needed the fact that the so if Z1 and Z2 are complex numbers, then Z1. Then they wanted the fact that the absolute value of Z1 plus Z2 is equal to the absolute value of Z1 plus the absolute value of Z2, if and only if the argument of Z1 is equal to the argument of Z2. So the corresponding picture is you have Z1 here, and if you have Z2 somewhere else, then you have a strict triangle inequality here. And so so in some sense, strict convexity can also be described as a strict triangle inequality, in the sense that x plus y is equal to x plus y, if and only if x, y are collinear, and possibly 0, depending on your definition of collinear.
And there's a sign issue.
Yes, there is a sign issue. That's why yeah, you need co-linear on one side. You can't have a x and minus y. If yes, so it's like on the same ray. And as it turns out, Yuri Kudryashov also needed strictly convex spaces, but I'm not sure what for, because nothing has been out yet. I just know he needed them. And Yuri brings me back to something to what I was just saying about namely that there's actually another construction, much more recent. It's actually from 2017, something like that. Yep, let me move here. By Elkin. Mm, 20 something. And the idea is kind of the same, namely to look at the sphere in some sense, find a subset of it, or decide on a subset of the naturals from it, and use the fact that the sphere is strictly convex to get that there are not there are no arithmetic progressions in the resulting set. But instead of looking at the sphere, intersecting it, mapping it to the naturals like this, we'll do something slightly different. We'll consider the box from 0 to 1. So like this is will be 1, 0. Yep. As the torus, we'll take a bit of the sphere in there and we'll thicken it a bit. So, I mean, okay, let me represent it slightly differently. Let me yeah, thicken it slightly more. And now, instead of intersecting, we'll take well, it's kind of a linear map, except that it's looping around, so I guess it doesn't really make sense of talking about linear maps here. From the naturals to this space, such that the reason of this is irrational. And because we were considering to be on the torus, we make it loop around. And so this is one of the basic results of ergodic theory. That such a map will be dense in the torus. So we know how many points will end up in this region. The density is basically it will be the ratio of the volume of this region with respect to the entire torus. So if we pick out these things, we look at the points which end up in this region, and those will make up our set. And you see that they do have arithmetic progressions of n3, but with some slightly technical arguments, you can show that actually you can remove not many of them and become arithmetic progression free. And so with all of this in mind, this gives us a bound of so this is a bit ridiculous because it's n over e to the o of root log n times ln of n. And so this is no better than Behrend. On first order. As it turns out, on the second order, it's better. But for something which came like 17 years later, you would have expected a slightly more improvement. And so what's interesting in this is that this requires, if we want to formalize it, this requires torus integral, which is something that Yuri provided recently to MATLAB.
Is a linear bound proven to be impossible by Szemerédi's theorem, or is it possible that both can exist?
No, it's the bound from Szemerédi's theorem is little o of n. So
it's impossible to have a construction which is linear.
Yes. Actually, I think that the best bound, the best upper bound today is something like n over it's o of n log n over log n, something like this. So this definitely rules out linearity. And so this is a very interesting problem because it's purely combinatorics, but the best arguments that we have to provide lower bounds are all rooted in geometry. And so this is one way in which combinatorics is benefiting MATLAB, and MATLAB is benefiting it back. So I have another example, which is Ruzsa's triangle inequality. So the Ruzsa triangle inequality is an inequality with which can be interpreted as a triangle inequality with respect to the correct metric. And this is concerned about pointwise operations on sets. So the idea is that if you have a set, if you have a set A, so let's call that A, and you have a set B, then you can define A plus B as all the different ways of writing, well, as small a, sorry, let me write it properly, as all possible sums from one element of A and one element of B. So for example, A plus B in that case will look something like this. And you see in that case that the size of A plus B is the size of A plus the size of B times the size of B. But of course, you could have collisions in some sense. So the question now is, can you find a bound on the size of A plus B given A and B, and possibly other properties of them? Because typically, if you take A and B arithmetic progressions, well, mostly concerned about arithmetic progressions in additive combinatorics. So if we take A to be this arithmetic progression and B to be another arithmetic progression of the same reason, so let's call this D and this is also D. Then you see that A plus B will be also an arithmetic progression, and it will be so it will be an arithmetic progression. So I took let's say I take 5 things in A and 4 things in B. So what do I get? If I sum those two, I will get this one. If I sum this one and this one, I get that one. So I have a copy of B, and then each one of them, each other element of A will only give me one more element of A plus B. So I have 5 elements of A and 4 elements of B. So in total, I get 8 elements. So in that case, A plus B, the size of A plus B is equal to the size of A plus the size of B minus 1. So let's call that D as well. And you see that this is actually pretty small compared to the size of A times the size of B. So there are many things like this around this area of mathematics. And in that particular case, I'm interested in this statement, that A minus C times B less than A minus B times B minus C. And actually, I'm not really interested in this statement, but rather to the consequence if you replace the minus signs by plus signs. Because this is also a theorem slightly later. Here. So this is the same thing as before, but with plus signs. And we cannot prove it as easily as the first one. We need something in between, which is called Plünecker-Petridis, which is this slightly technical lemma. And I do not really care about the statement. I mostly care about the proof. So for example, let's just isolate this thing. We do not care about the definition of A and C. I just want the definition of A prime and this and that. Okay, so A prime is defined as sorry, it's defined as the A intersected with A plus C minus X. Okay. And now I want to show that A prime plus X is equal to A plus X intersected with A plus C. So what do I want to do? I write A prime plus X. That's equal to A intersecting with A plus C minus X plus X. Okay, so we have this plus and we have this intersection. They do not commute in general, but because because this is a singleton, in an act of faith, we'll assume it does. So we get A plus X intersected with A plus C minus X plus X. Okay, so now I want this to be equal to A plus X intersected with A plus C. So there's an obvious thing to do. We have to cancel the minus X and plus X. And you're telling me, well, this is obvious. This definitely has to happen. But we are not actually in a group right now. All those are sets, or actually even thin sets. And if you look at S minus S in general, this won't actually be a 0. Whatever 0 means. And actually, we can make sense of zeros. What should 0 be for a set? If you add it to any other set, it has to give it back. So if we think about it a little bit, it can't be empty because S plus the empty set will be the empty set. So it has to contain some element at least. And if it contained an element different from 0, that would move it. That would make a shifted copy of S somewhere, and that's probably not what we want. So actually, we'll define 0 as a set to be 0 the singleton, and this is an element of our base type. Okay. So if you take, for example, S to be this, then S minus S won't actually be only 1 point. It would be like 3 of them. So we definitely cannot cancel this in general. We have to use the fact that this is that X is cancelable. But even then, that's not something. That's not a property of. Well, actually, until recently, that wasn't a property of the things less powerful than groups, which we call monoids. It just wasn't really possible to write it like that. So what you had to do was to write this A plus C minus X as the image of A plus C under the subtracting X operation, and the plus X as the image of this thing under adding X, and then composing the images and showing that this was actually the identity to get A plus C. And this was most definitely a pain. So at this point, I kind of rolled my eyes over and thought of a generalization I could do. And this is what I came up with. I made up division monoids which are so they are like a monoid. They also have subtraction.
Group law is addition.
Yes.
Uh-huh.
Or was yeah, okay. So I guess I would call that subtraction monoid if you want.
Okay.
Just to okay. to be consistent. Okay. So this will be an additive monoid. Not that it matters, of course, but yeah. So we have subtraction, negation, and want several things. One, something which is quite obvious from what we know already, is that well, okay, well, so A minus B, yep, is equal to A plus minus B. I mean, you could argue that you could even take that as the definition of subtraction, but of course, in MATLAB, that's not really what we want. We want to be able to fix definitional inequalities. that if a plus b is equal to 0, then a is equal to minus b. So if a has an inverse, then minus a is that inverse. What we're not saying is that minus a is always an inverse of a, because as we've seen, this is not the case. So we cannot assume this, and we were walking around it by like finding like the most powerful statements that we can get without assuming this. We'll also say that minus a plus b is equal to minus a plus minus b. Well, actually, we'll say something else because we don't want to assume commutativity. So we'll actually write it like this: minus b plus minus a, and we can get the previous one by commutativity if we have it. Okay. And minus a is equal to a. Okay, so like those are definitely true for groups. So we know this is a generalization, but if we think of it, so like with the multiplicative operation, this is also the case for group with 0. So for if we look at group with 0, it's
1 over 0 is defined to be 0.
What?
Is 1 over 0 defined to be 0 in a group?
Exactly, yes.
Okay.
So group with 0, okay, this is definitely monoid. It definitely has division and inversion. So I'm just doing the multiplicative thing now. This is also true by definition. And now if AB is equal to 1, then in particular, A and B are different from 0, because 1 is different from 0 from 0. So we can cancel. And A is equal to, oh, this is really unreadable, sorry. And A is equal to B inverse, which is what we wanted. And finally, this is same. This is the same idea. If A is equal to 0, obvious, because this will be minus B and this will also be minus B. Actually, yeah, we just have to, yeah, because minus 0 is equal to 0. Minus 0, sorry, inverse of 0, yes. Because 0 inverse, sorry, I should write it here. The inverse of 0 is 0. If B is equal to 0, obvious. Else, we can cancel. And we only need to show that A inverse times B inverse times B times A is equal to, sorry, what's it the wrong way around? It should be AB times B inverse, yes. Right. Is equal to 1, and this gives us the result. And indeed, for this, so this corresponding to that. And the final point, so if A is equal to 0, then 0 to the minus 1 to the minus 1 is equal to 0 to the minus 1, which is 0 again. Else you cancel, and it works again. So in that case, I wrote this thing for a very specific purpose, which was manipulating operations on sets. Because I showed you one example, but actually this PDF is littered with things like this. It keeps adding and subtracting stuff in different places in ways which are not compatible with the fact that a set is not a group. But you can make sense of it if you consider it as a subtraction monoid.
Yeah.
Yes. Am I running out of time?
Oh, I don't know. But I was, when you showed the original set example, I kind of had a different generalization in mind, which is that you were using a special element that cancels. You were using X, right? And you can say that there's the sets, and then you have a group action of the elements from the set. So the set map, or the elements map via the singleton map to the set, and that mapping preserve, like the image of that map produces elements that have good properties, that have cancellation and so on. So that seems like, even though the full structure is this monoid thing, you have some kind of, I don't know, like a centralizer situation where certain elements look better than others.
Yeah, I mean, this is actually a problem in MATLAB for a different reason, namely that actions only act on the left. So I cannot add stuff on the right, and this is very annoying. I mean, I think Eric is about to make that work. Like, I mean, I'm pretty sure you can already multiply stuff on the right, but it's not really user friendly. And like, do I want to write this as like, how do I even write this? Like, X. No, it's not X. No, it's not this. It's op X V add minus, I guess it's the same, op minus X V add of A plus C. I think that should do the right thing. But like, you see that it's been mangled around. Like, why is this minus X on the left given that it should be on the right? And like, the notation really doesn't deserves really makes a great disservice to the readability of the proof.
Are these commutative? Is this plus operation?
Yeah, these are sets of reals. Right?
Yeah, right.
Yeah,
Can we just put things on the right side?
Yeah, no, this is scalar addition. This is how it is defined in MATLAB.
Right, but we don't need the op, right?
No,
we multiply it on the other side, but it's fine because they're reals.
I mean, sure. Here they are in that case they are reals, but like if you take the Ruzsa triangle inequality, well, I'm not actually using it there, but if you take the Ruzsa triangle inequality, if you take the Ruzsa triangle inequality, can I find it, please? Where is it? That's it, I lost it. Well, anyway, the Ruzsa triangle inequality is actually true in any group. It doesn't need a commutativity. Yeah. So this is actually any group. And it would be a shame to like restrict our proofs to commutative things, because our notation is shit. And moreover, that means that you need to use commutativity. Well, you will need the applications of commutativity more often, just for the sake of writing the thing down. If that makes sense. And I mean, like, even forgetting about this, I have problems which cannot be solved using this approach. Namely, at some point, I do need to use the fact that, well, yeah, just take this. Okay, so it's obvious, but it's actually not. It was actually not to MATLAB a month ago. It's obvious that if you know this, that you also know that A plus C times B is less than A minus B times B plus C. Because I've just replaced C and minus C, right? But to actually do this, I need to rewrite A minus C as A plus C. And like this is a property of additive groups, not a property of monoids. So this actually doesn't make sense, or didn't make sense. And same, like if I could also replace B by minus B to get A minus C times B is less than A plus B times B minus C. So we just a plus here. But then I would need to rewrite rewrite minus B minus C as is equal to minus B plus C as being minus B minus C. And like it just goes on to like the list of equalities which I would want to be true but which weren't which weren't easily accessible to Mathlib, just goes on forever. Like it's literally like this over and over. Does that make sense? So I don't actually see what's going on in the room. So if there's no one to answer, I guess I will just go on. Okay, so maybe it's time to actually show you some lean code. Okay, this is them. I had prepared all the Gitpod things, but of course they tanked out. Okay, so this was Behrend. Okay. So so this is the proof of Behrend's construction, including the numerical calculation at the end. So we first start by defining. I would like to do without it, but we first start by defining the box, which is the thing I talked about here. I need to restrict to this box to then make sense of carrying over. It's fine. I don't do much with it actually. Then I define the intersection of the Euclidean sphere with n to the d. And n to the d, I guess this is actually n to the n here. We don't model it as the functions from fin n to n, which is pretty standard for Mathlib. Then we define the crucial thing, which is the map from n to the d to n, and we show that it's well, I think it's even a linear map, but I only need to show that it was an additive monoidomorphism. So you define it as what I did. Where was it? It was here. Yes. So A0 plus A1 K plus E D minus 1 K D minus 1. This is this is this definition verbatim. Okay, so fine for this. And then you show the fact that it doesn't carry over, which is this thing. Well, you can also show that injective. I guess that's useful. And then you show that it doesn't have arithmetic progressions. And so this is the interesting bit of the proof, because to do this you use this why is it not loading? What a shame. Okay. So you have this sphere in n to the d, and you want to show that it doesn't have arithmetic progressions. The property of not having arithmetic progressions of length 3 is called being a Simon-Spencer set. So we have this predicate at Simon-Spencer for sets which are which do not have arithmetic progressions of length 3. And we have this lemma at Simon-Spencer here, which you would never find in a textbook because it mixes up combinatorics and geometric notations. But it tells you that the sphere, the Euclidean sphere, is Simon-Spencer. And so what this lemma does is to get the fact that the Euclidean sphere is Spencer to the fact that the sphere in and the corresponding sphere in N2D is also Spencer, which is obvious, but actually it looks like it's like, yeah, it's 9 lines and it's probably like 8 too many, but yeah, fine. And so once we have this, it's really just a matter of putting the things together to get this this result, which tells us that the minimum number of the maximum number of elements less than this big N, such that there are no arithmetic progressions of length 3, is at least the cardinality of a sphere of a somehow related size. And then we have so this ends on line 200, and then we have about 350 lines of calculations to show this result, which is the one we care about. So actually, when I showed the O of root of log n, which was here, yep, sorry, this can actually be taken to be -4 of root of log n. And actually, you can even make it to be so that the general expression is 2 root 2 to the 2 root 2 of log n of root of log n. Sorry.
Presumably, all this was known.
Yes. Yes, absolutely. This is, I mean, this is known from the 1946, and people had fun figuring out the correct constants. But as it turns out, I mean, it's quite expectable that this 2 root 2 bound is much more annoying to prove than this. So this should be 4 if you are still on the denominator. It's much more annoying to show that this e to the 4, because I mean, because numerical calculations. I mean, if you have a look at what it requires, you need advanced stuff like that e to the 4 is less than 64. Ooh. But no, actually, like things like what was it? Yeah, like we will need to manipulate stuff like this, like the ceiling of root of log n and the floor of this horrible thing. And those are generally not easy to deal with, because like if you were walking over the rails, you could just optimize and say that you reach the minimum when the derivative is 0. But we're actually walking on over the naturals, so all this also this derivative intuition just vanishes, and you have to like use stuff which is close to this, and it doesn't and it does make the bounds worse in a way which is hard to deal with by hand. I mean, once again, like I guess Mario left the room, but
he's got to catch a plane.
Too bad, because we definitely want more automation for stuff like this.
We were just talking about this over lunch, actually.
Yeah, I mean, I guess everyone is talking about is telling him about this, because Northern is great, but it's still not enough. Like, we want more. Like you see this big paragraph. Like, I wish this was just one. I wish like this was one practical or something. It shouldn't need like 8 lines. And I mean, probably even the entire proof. Yeah, the entire proof could be it could probably be automated away.
Because when you just write down what it means, it's 2 lines of calculation on paper.
I mean, it would be 0 line because nobody cares about the calculations. But the one paper that was actually explaining the calculations, I think took 4 lines at most to prove this. and it was like putting in a lot of detail, and it was an effort from its part. So yeah, there's definitely improvement on the side of automation, which would be possible, because this is what makes the proof annoying. I mean, like if you once again, if you compare the mathematically interesting part of the proof is like it's not even 200 lines, because it starts actually on line 63. It's like 150 lines, and then starting from line 200 to line 550, this is just boring stuff. So there's a ratio of 1 to 2 interesting to non-interesting things. So this was Behrend, and I can also show you the code for. Can I? Yes. No, I cannot, because it hasn't loaded. No. Sorry. So we'll open another Git pod. New workspace. I'm not actually sure how to access them like this by hand. I want the. Do I just need to copy it? Okay, fine. Tree adds Plunaka Ruzsa. Okay. I guess I could also mention as a third example of how combinatorics can benefit the greater MATLAB, the unit fractions project by Bavik and Thomas Bloom, because in that project they have formalized like quite many standard results in analytic number theory. So this is the blueprint of the project. And like one of the first items is this bound on which is called Merton's estimate for primes. And like most of these results, namely, for example, there's the C of Justin. This is interesting. Which one is it? Blam, 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 blam. Yeah, like this one. There's also something called I cannot find it, but yeah, most of these items are actually so this thing, yeah, Chebyshev's estimate, and all those things are like things which are like results which you would find in a standard analytic number theory textbook, but they aren't yet in MATLAB because nobody so far nobody needed them. So the fact that unit fractions actually wrote them means that in maybe some month time they will be available to everyone. This sounds like it could be the start of a greater thing, because many different results in analytic number theory, both from the number theory side and the combinatorics side, need such estimates quite routinely. And of course, they are assumed because nobody is gonna include them in each paper. So whenever you read a paper, you should have a look at which ones of those estimates they depend on. And odds are, well, right now, odds are that they won't be anywhere in MATLAB. But in some month time, that might be the case that actually we have them. Okay, so I wanted to show you to end. I wanted to show you the proof of the proof of Ruzsa's triangle inequality, which is pretty short, and mostly the proof of Plunaka-Petridis, which is the thing which, if you recognize, this is what I had trouble proving. And now showing that a prime plus x is equal to a plus x intersected with a plus c is literally just one line of calculation and 3 rewrites. And I mean, I feel like it could even be easier with automation, but it's short enough for my purposes, and I'm happy with it. And if you look at the info view, like the calculation is literally what I wrote down, and it follows it verbatim. And yeah, I mean, this is the one calculation I wrote down. And if we, yeah, I'm now deriving the other triangle inequalities from the first one. So for example, there was, so this is the first one. And so this replaces b by minus b, right? We have a minus c, but instead of a minus b, we have a plus b. Instead of b minus c, we have b plus c. And because we're taking the cardinality, this is the same as if we had a minus sign everywhere. So if we look at the static state, it turns a plus b into a minus minus b, which was the hard bit. Turns the cardinality of b into the cardinality of minus b. Same for b plus c. It distributes the minus over the addition. Writes it as minus c. And then it's exactly the previous statement. Ta-da! And I think that's it. Any questions?
Thank you very much. Let me stop recording.